know that we have these general relativistic magnetohydrodynamic codes that exist. Namely, the one that Chris has been working on is this Cosmos++. It's fully general relativistic. Obviously, we're vecting the magnetohydrodynamic codes. Two things that I'd really like to point out, especially specifically to these simulations, we have no prescription for radiative cooling, and also we don't capture heat properly when it comes to magnetic reconnection or advected velocity fields. So that's going to be important to keep in mind a little bit later. These codes are similar to some of the other stuff we've seen out there. I know Mommy's going to be presenting, I think, right after me. So we'll hear more about their similar codes, which are pseudo-Newtonian. So kind of following in that vein, we also know that QPOs exist. When we look at observations of these black hole binaries, okay, you guys are all experts in this, so we don't need to go too much detail. Obviously, they're divided into the two categories, the low and high frequency. The primary difference being that the low frequency QPO's frequency varies according to the disk flux itself, whereas the high frequency QPO is stable even between successive eruptions of the steep power law state. So kind of what does this maybe tell us a little bit physically about these guys? First of all, we could probably say that this low frequency QPO might be tied to the actual disk dynamics itself. If the inner edge of the disk is moving in or out or whatever, that might affect the low frequency QPO's frequency. Whereas if the high frequency QPO is due to some sort of space-time geometry, it would then be understandable that it's more stable, or that it is stable. So anyway, with those two in mind, it seems like a logical progression then to just say, okay, well, let's look for these QPOs in our general relativistic magnetohydrodynamic simulations. But that's actually not necessarily the most straightforward or even intelligent thing to do without first looking at some of the issues that might, or that we might see when doing that. So first of all, we know that these QPOs exist largely in the harder side of the spectrum, in the power law component of the spectrum. And so without these proper heating and cooling methods in the simulations, are we really producing some sort of a corona that could effectively Comptonize or Compton upscatter some of these photons? The answer is no. We don't really see the generation of a corona in these simulations. There might be a hot backflow that could be responsible, but nonetheless, we really don't think that there's, at least in our simulations, that we're seeing the development of a corona that could be responsible for those Compton upscattered photons. But even if we did see that, we still have to wonder, well, would the dynamics that are responsible for the QPO necessarily be in the disk, or would it be in that corona that we're not seeing? And so it's also, unclear that by simulating the more kind of disky part of one of these objects, we would even still see the QPO if in fact the dynamics were in the some sort of a corona itself. Again, assuming that though, and we're moving on to assuming that's all working, do these the disks that we're simulating in these codes properly even represent what would be the steep power law state? Because we don't see these QPOs in some sort of thermal state, right? So even if it depended on the generation of a corona, it's not necessarily clear if just simulating the disk, or even if this disk that we're looking at is exactly what would be present in the steep power law state. So anyway, we're not going to worry about all those considerations. We're just going to assume, yes, we've got this thermal kind of part that we're simulating, and in fact, the QPO will be present in there. So we'll just kind of proceed with abandon and hope everything works out. We've run a handful of these simulations. Today we're going to be looking at primarily data from 4 of these simulations. These are, again, fully global, general relativistic, magnetohydrodynamic simulations. We're putting these disks into a Kerr space-time with a spin of about 0.9 or f0.9, and seeding the disk with initial fluctuations and some poloidal field. So these 4 simulations that we're going to be talking about most are going to be a medium and a high-resolution simulation, particularly the first 2 that have no tilt, and then a set of 2 that do have a tilt, where the angular momentum of the disk is not aligned with the spin of the black hole. And we'll see if that also produces anything interesting. So first I'm going to kind of build up your hopes. It's an exciting thing that we see When we look at our medium resolution runs, where on the left is the untilted simulation, on the right is the tilted simulation. This is a plot of the power density spectrum as a function of radius and frequency. So warmer colors will represent higher power at a specific frequency at a specific radius in the disk. The overplotted lines are the orbital frequency is the solid line, the ISCO is this dotted line. Outside of the orbital frequency are the harmonics of the orbital frequency, and then inside is the vertical epicyclic and the radial epicyclic frequencies. So in addition to kind of seeing, I know we kind of talked about this a little bit yesterday, some blobs maybe that are following these orbital frequencies and its harmonics, one of the exciting features that sticks out in these plots are these vertical lines of power, which indicate a large amount of power at a specific frequency over multiple, or over a range in radii, which we hope would be some sort of, that's what we would call a QPO, right? I mean, that's an extended oscillation in the disk, all orbiting coherently at one frequency.
So these are 3 snapshots?
Perfect question. This is the density, this is the radial velocity, and this is the vertical velocity, polar velocity. And so that would, we're not going to talk about it too much today, but that would help us maybe diagnose between different type of modes.
Could you repeat density?
Density, radial velocity, and then polar velocity.
She doesn't tell them how that's been averaged, or
These are all shell average quantities, and so, but it's all the Fourier transforms and power spectra are calculated before doing any averaging. So this is the average of the power spectrum on a shell, which might have issues because, well, not issues, but it would not tell us where the QPO is vertically, but we'll talk about geometry in a little bit. So either way, this kind of points out where these QPOs might be, at what frequency, and over what radii. Anyway, so now we're all excited, we see QPOs, we move on to our high resolution simulations, and we don't see them. So, I mean, there's obviously one important difference between this simulation and this simulation. You see a lot of red over here, right? So in the tilted simulations, is in looking at the Fragel and Blaise recent paper, there are these plunging regions that are about 10 gravitational radii inward. That's all due to that. There's maybe some stuff here, but it's all really small and weak, and so we will maybe talk about that a little bit in the future. But right now, it's obvious we don't see any of those big spikes that we saw in the medium resolution simulations. So when obviously this is tied somehow to resolution issues, that kind of asks us, well, what's the best way to proceed? What exactly are we looking at? I think then to really look physically at those QPOs we saw in the medium resolution run will help kind of illuminate the problem. So on the right is a plot of the real and imaginary parts of the Fourier transform, the time domain Fourier transform of our simulations. And so we can kind of think of that as somehow an eigenfunction of these oscillations. Namely, if kind of you start at one beginning period of the oscillation, you might start with this picture in density, radial velocity, and polar velocity. A quarter of a period later, you would then end up with this guy. A quarter of a period later, you'd end up with this guy, but flipped over, right? So just the negative sign of that. Anyway, so the pi/2 symmetry that you see between the real and imaginary part indicates that this pattern is actually rotating rigidly. It's not just the artifacts of producing some ugly time spectrum or time evolution. Furthermore, a relationship between the density and the radial velocity indicates that there's actually vortex-like motion around these structures. And finally, although they grow fairly quickly, they're stable for sure by about 10 orbits in. Well, what does this tell us? It seems a lot like an inertial mode, right? Some sort of global inertial mode that's developed in these simulations. But that seems to conflict with work that's been previously done a while ago in 2006 by Ayres, Blaise, and Turner, and then recently in the Reynolds and Miller paper, where they said that these inertial modes, these G modes, should be wiped out by MRI turbulence. So the fact that we're seeing them in a medium resolution simulation, but not in a high resolution simulation, must say something about the MRI. So if we look at the resolution of the MRI, basically taking the how many grid zones per critical MRI wavelength, we'll see that in the medium resolution runs, everything, even all the way out to 100 orbits, is very under-resolved. So it looks like the MRI is not acting appropriately or being resolved appropriately in the medium resolution run. Whereas in the high resolution simulations, even 10 orbits in, you have a very well resolved MRI. So with that in mind, it seems that really to accurately observe quote unquote, these QPOs in a global general relativistic magnetohydrodynamic simulation, you need to make sure that the MRI is sufficiently resolved. And here we're kind of saying this roughly 10% of the MRI critical wavelength. Furthermore, these simulations seem to support the idea that the MRI kind of squashes any global inertial mode. And then we didn't talk about it so much, but high-frequency QPOs may or may not exist in these simulations. Those are kind of those really weak things I pointed out in the high-resolution tilted simulations. But at this point, again, they're kind of an unknown significance, and their origin is definitely not understood. I know that I think there's, in light of discussions yesterday, we might want to talk more about those and look at the pictures. But anyway, so we can definitely talk about that in our questions section, which will start now.
So, my understanding is that the inertial gravity modes are essentially related to alpha n waves, and then the MRI is a slow MHD mode. So it's not obvious to me why having the MRI acting in the flow would get rid of the inertial gravity alpha n mode. So what's the argument for this?
So you're asking why the MRI should kill the inertial modes?
Yeah, what's the argument has been, you said there was this Reynolds and Miller. Is it the reason of the simulation, or is it a more fundamental?
So,
if I may make a comment on Reynolds and Miller, they actually said they're unable to state whether or not it kills it.
okay. If they don't say it,
Is it from simulation, or is it a fundamental?
theirs is from simulation, their recent simulations, correct?
Yes.
And then this 2006 paper was from shearing box calculations, correct?
Yeah.
So it's, I think, all simulation.
So you don't see them.
Here's the physical argument, if I may,
Please.
because I'm the one who has strong
Yes,
opinions about
your name's
this.
on the board, so.
Yes. So you're right. The inertial modes are not the same thing as the modes that give rise to the MRI. But nevertheless, the MRI produces strong turbulence on a time scale of order the mode frequency of the inertial mode. So you're trying to sustain a wave, a mode, in a medium which is bearing large forces on the mode period time scale. So I just don't believe that you can sustain such a mode. And when you simulate that, you don't see them. You really don't. And yet you see high frequency modes all over the place.
It's like you're sound waves and convective, you know.
No,
Alpha is faster than slow
No,
mode.
sound waves are not. Sound waves do have much higher frequencies and a much higher propagation speed. So when you're talking about a trapped sound wave, the medium is essentially frozen. The turbulence is essentially frozen as the acoustic wave is propagating back and forth. But that's not true.
You're saying there's not enough separation of speed between
Exactly.
alpha and slow mode.
Exactly.
Okay.
Yeah.
So that's your idea.
Yeah.
Well, if I may comment on that.
Go
I
ahead.
have no opinion on the simulations, but in the real world, for real disk, the timescales are identical also. Presumably, if the disk is turbulent, then the turbulent timescale is comparable to the actual observed frequency. So I don't think it is generally true that if the timescale is the same, then no global modes may be.
So G modes though, their mode periods are characteristically less than the angular frequency.
I don't know.
Right,
I
and
don't
the
know
angular
what they are.
frequency is the characteristic frequency of the MRI. And so I'm not saying that, what I'm saying is that QPOs are not G modes. I I'm not,
I'm not saying
there are
what
lots of
kind
other
of
modes
modes
that can
they
exist
are,
in
I'm
the
just saying
disk,
they
yeah.
have the same time scale.
Yeah.
Presumably as the
Yeah.
turbulence.
Right. Right, but not less than the turbulence. Not slower than the turbulence, and that's the point.
Yeah, I was just curious, in the story simulation, you have a transient phase where you develop the MRI, and then you start accreting, and then after, I don't know, a few discs time, presumably you go into a phase where you have to decay, basically. You're not putting mass in, so they are all, in a sense, transient simulations. And so I'm just wondering if, when you show us this PDF, on the low frequency side, there will be, at some point, you're going to hit a wall just because your thing has spread and it's changing character. Do you have an idea whether, I mean, when you do your averages, when you look at things, how many orbits, I guess, do you integrate and you do this average over?
We've looked
But
at...
That could be changing with resolution. Well, it's not obvious, I guess.
Right, so to rephrase your question, are you asking me what, if you look at the entire time domain of the simulations and it did a whole Fourier transform over all of that versus just the latter part,
yeah,
and comparing different...
the latter part, if you integrate too long, is a viscously decaying flow. It's not quasi-steady state flow. I mean, there's an issue that these are not. You're trying to do quasi-steady state with really non-steady state simulation. So it's a little bit of an issue there.
We haven't. I don't include any of those cutting up the time sections and then doing producing these PSDs. I don't have any of those plots in here. We've done that, and it seems mostly to affect the width of this QPO, and then, like you say, obviously you lose low frequency information, and even things like this, feature right here. A lot of that is dependent on what parts of the simulation you include, and so I think at least for the arguments here, these still are present in all of them. It's not a numeric Fourier transform effect or a ringing type thing from the initial conditions.
I have a remark on quasi-steady state. It may be that real QPOs are not connected with quasi-steady state. We do see QPOs emerging when the systems are very violent, like undergoing a transition from one state to another state. And it may be that we theoreticians were looking for these QPOs in the wrong places. That is the same thing in numerical simulations and the same thing in analytic theory. In analytic theory, we were looking for oscillations of systems which were in a very strong, stable equilibrium. Maybe that is a mistake, because in theory the problem is that if we do this plot, here is on the vertical axis the amplitude of perturbation, and on the other axis is the kind of in frequency how far from resonance we are. There is something which we call the Arnold tongue, where there is the instability. And the thing is that that is what Irka Horak did for a particular resonance, which may be or may be not connected to QPOs, but that is a generic feature of all these kind of situations. Then there is a time for growing this particular instability, which starts with extremely long growing times. And only very up in this Arnold tongue times are interesting. But then it means that the amplitude, initial amplitude, is huge. So maybe in order to get these QPOs, we really should shake whatever it is, this transient torus, or quite a lot. And therefore maybe the reason that we do not see these QPOs is that we are too gentle to our models. We are not shaking these models sufficiently strongly.
Chris, you do need to kick it.
It's maybe
But then on one of your transparencies, you kind of ask somebody from the public to ask you about transient torus, and I am doing this. As a
Okay.
church. Please tell us about transient torus.
So this is that plot I put up before that I was kind of hemmed and hawed about. Well, maybe maybe that is some sort of a frequency, because again, it is this vertical spike over an extended radius set of radii. So what might that be? It actually doesn't project that well, but on the right is the same kind of eigenmode type plot, and you see a ton of high M, if you will, high harmonic structure at a large number of radii. Now, these plots say that this high power region is primarily less than 10 radii, which is this very inner region. That's giving rise to the majority of the power. And so it's not necessarily clear if that stuff on the outside is just either fluff, or if it's some sort of just the non-axisymmetric not perturbations, but things going on in the outer parts of the disk that are they always will have components at various harmonics of the orbital frequency at those radii. But either way, it's I don't know if you can see those from all the way over there, but on the other hand, in light of yesterday's conversation, they're not circles necessarily. They do kind of have some sort of spiral shape to them, and so I don't think we've really thought too much about what that might be, but maybe there's some discussion that can take place.
So you have an answer.
You flash a sequence of slides, and I've seen it for a fraction of a second, but it looked like a transient torus to me. It was very transient.
Oh, I'm sorry. This is what you're asking?
Yes.
So these are just slices through vertical slices of the disk as a function of time. This is the two orbits in. So looking at what you were talking about, a torus that's starting way out here, and then you've got a whole bunch of junk that falls in and stuff that goes on like that. At about, what's this at? My plot's too small. This is at 6 orbits, and this is at 10 orbits. That's just a blow up of this last guy. I kind of included this in that we might consider calling this some sort of an inner torus, given that it's significantly inward of where the torus originally started. I'm sorry, I've forgotten your question now.
But you answered it.
Okay, good. Then it doesn't matter.
Can I emphasize something else? Just
Sure, please.
Because Barbara's here. If you could go back to the previous slide. So, a response to the fact that to my
Skepticism.
Yeah, to my prejudice against G modes has been raised by Gordon and Barbara, and that in order to excite them, and by Shoji Kato as well, that you need to impart a tilt or a warp to the disk. Or a way of exciting them is to impart a tilt or a warp to the disk, and you can excite G modes. And if you don't have that, then all you have is turbulence killing them, and they don't have a chance to. So these weak features that you see are still their frequencies are still inertial mode frequencies, and this is a tilted simulation. So
this one at least is correct, because it's inward of the.
This might be the. I mean, is. So I'd like your opinion on this at some point.
What you said.
Yeah.
I'm guessing it is.
Well, it's an inertial mode and it's a tilted disk, so it is. And I mean, they look like inertial modes, but it's not clear that they're very significant. But I mean, I see discrete features there.
I have a question about these warp disks
Yeah.
and inertial modes. Would you both agree that there is, however, a big difference between these simulations and what you do with Gordon and what Shoji Kato is doing? Namely, that your warp is put by hand. It is not. It is always there. If there is something which would kill it, like, of course, in these simulations you have the whole physics, and you put the warp at the beginning, maybe it will disappear later. But my understanding is that in these works by Shoji, Gordon and you, this warp cannot disappear because it is always there by construction. Am I correct in this?
Yes.
So it is like a source of external perturbation.
Which is what we've got here, but.
No, because you just
No, no,
you
no,
started
no,
with
no,
a
no,
torus
no,
that's at
no.
a
You
tilt.
have
and then-
only initially, and then you let
No,
it.
No, but
Mark,
it's
this is not a,
so-
this is
Ah.
not a coplanar disc that part of it's, this is the reservoir
Oh,
outside is
okay,
at a
okay,
tilt, and so it's
okay, so it
continually
is the same
feeding it
thing.
in.
Yeah. Okay.
Uh,
But okay, go ahead and then Michał.
well, I should actually know the answer, but so, and I probably asked you guys this, the epicyclic motion that we see in the disk doesn't show up with any power in the power density spectrum, is that what I?
No, because its frequency is the precession frequency, right?
And so it's just,
I mean, it is there.
That's
it's,
off.
It's, but
Okay,
it's,
this is what I was asking you
it's
yesterday.
the duration of the simulation.
Right, okay.
So
Alright.
it's way below the frequency now.
You mean it's the lens tearing frequency? The 3
Well,
hertz.
it's, we see this epicyclic sloshing, I mean, that was actually I think the plot you skipped over a couple back, as you go, I think you.
Tell me when to stop.
This one.
Uh-huh.
That's actually a plot of residual radial velocity put over top of, on the left is the tilted simulation, on the right is the untilted. And so on the right you see it's basically just turbulent motion, but on the left there's actually a coherent circulation pattern that's set up in the tilted disk. And but you're saying that circulation frequency is the,
No, it's the orbital frequency. What am I saying?
yeah, so I don't, it's not the.
So no, right. You're right.
What are the colors? So like it's up to
Yeah,
The
so-
colors, red just means radially moving outwards, and blue means radially moving inwards. So on the plot on the left, everything in the upper half of the disk is basically moving radially out, and things on the bottom half of the disk are moving radially in.
radially with respect to the black hole.
Radially with respect to local coordinates, but essentially.
Is it a closed
From-
circulation? Is it that you don't show the rest of the torus and it's a closed circulation?
Uh,
Right now it looks a little bit.
This
open.
is not the whole torus.
Right, this is the interior
But
region.
it's a closed circulation?
What it actually is that everything in the upper half, it's actually epicyclic motion. The stuff on the upper half of the torus is actually, what do you want to say? Its apocenter is on the, well, it's moving radially out all the stuff.
moving on elliptical orbits.
Yeah, the upper half's moving on an elliptical orbit, the lower half's moving on an elliptical orbit with them shifted in phase by 180 degrees.
Ah.
So while one half's moving out, the other half's moving in.
I don't-
Right, so they're sliding past each other at the midplane. And so there's some.
I don't
Right, so
think
it's
we
not a
necessarily.
closed
It's not a
like
closed
this,
formation,
it's
yeah.
like-
Okay, so now I understand. So it is the precession frequency. It's because when you put a probe into the disk, everything is moving out until the torus is precessed around, and then it's now moving in at that
So it-
location.
Okay, all right.
So
So it
it's,
would be-
when you follow a fluid element, that it's moving it's moving in and out of the orbital frequency. But at a fixed location, it requires the entire precession frequency to see that
To
change.
see that change, okay.
Well, and I don't think that because you do see the inhomogeneities in the flow moving past your probe stuck at one point at the orbital frequency. I mean, there's definitely a larger power along and that's what I've always been calling blobs. And if they're not a pure N-1 mode, then, or if it's any type of shape, then you're obviously going to get power at the harmonics also, which we do see.
Can you-
That's all that simulation coming back to your.
Yeah, can you go back and show that scissoring motion again? Just
Yeah.
because I think everyone should understand. You haven't told the difference between the left and the right. So the left is.
Chris did.
Oh,
Oh,
Just that
okay,
this
right
is the
is-
untilted simulation, and so there's no
Oh, you see
coherent
the turbulent
velocity
motion.
structure set up. It just looks turbulent, whereas over here, because of the tilt, you get this much more ordered flow.
This is a big deal.
Mhm.
I mean, this looks significant.
Yeah.
And why there is no turbulence?
No, there
There
is.
is.
There is.
Right, there is turbulence under that, it's just this motion. Right.
But it's still that maybe you should move your curve up and down. Right? It's not precession.
Right? No, but
I mean, if you tilt your probes, right, they go at a specific frequency.
I think we should have probes that are following the precession, maybe. I don't know. I don't know. But,
Okay, Michał.
Yeah. Could you shift the slides forward?
Forward.
Forward, yeah. That was this one. So, seems to be quite convincing that you don't see any QPOs or something a little bit.
Seems like it.
Yeah. But then on my experience, where you spent this money, some time to analyze her simulations, and I'm sure in a few minutes her will show this kind of radially resolved power spectrum, and it will look like this one. So you don't see any particular oscillation. But then if we assume something about radiation and calculated the flux which emerges from her simulations, that we surprisingly revealed the QPO. And that was because there is some non-axisymmetric structure in the simulation, and that's what I see on the right side of this, this slide, that you have the same. And also, if you analyze local quantities, which you calculate, like, I don't know, mass accretion rate, you plot the power spectrum of this, you don't see anything interesting in the power spectrum, such as slope.
Correct.
And if you analyze the flux, due to this non-symmetric structures, you will have something which looks interesting.
How dependent is that on what model you assume for the radiation? I mean,
It sort of depends on the model. But
you're
not
doing
that
like
much.
you're doing like Bremsstrahlung or something where the overdensities show up as.
Yeah, but I think that in the point which Michał makes, it doesn't matter. It is that you have this radiation, whatever the reason for this radiation is, that it is emitted with a medium which has some velocity pattern. And then when you see this local velocity patterns through this ray tracing, which Michał is talking about, then more variability power appears. So it is not that very important.
Well, but some things would be more sensitive to, say, a density per. Some models of radiation would be more sensitive to density per.
Yes, that's right.
than
Yes,
others,
that's right.
but-
But the key point is here the bending and boosting. This is actually the rate.
This is only this effect only amplifies the modulation, but the modulation is still there.
Even if you don't do the
Yes.
so
Yeah, if you do it Minkowski space, it's still there mainly because of the
So is what you're saying, and I'm sure you're going to address this in a second. But the modulation is still an oscillation in the disk. It's just that through ray tracing you're amplifying this. It becomes much more significant. But so you have then, after you do this, you're then able to go back and identify what might be going on in the flow itself. It might be producing this oscillation,
Yes.
but there is an oscillation in the flow.
Then we did a similar figure to this, and then we plot specialties of power spectrum. So we identify the places where the power comes from, and then you see, if you look at the image, that there is really something interesting structures in this place, like what I see over there, some high-end modes.
Okay,
I think,
coffee break.
so I think Michał is offering to analyze your results.
Yeah,
If you can find QPOs in these
Try
simulations,
that.
I would love.
There are QPOs in the simulation. You don't know yet about it. Coffee break.